So I'm taking care of the temporal and spatial dimensions. Okay. If you have questions, please ask them. I'm assuming some stuff that maybe I shouldn't be assuming, like familiarity with this. So if I've lost you, please just ask the question. All right. Unfortunately, waves often get left out of 1600 because they're right at the end and we're all out of time. But it's not good because now I have to go back and explain waves, which I don't have 2 weeks to do, right? Which is what we really should spend on it. But that's okay. If you have questions, please ask. It's okay. If you're lost, other people are too. I'd rather take time to answer it than everybody get lost. Okay. Well, the good news is, once we've talked about this, there's a lot of talking, but you can actually just read off information from these equations. We'll show you an example, but first let me say, this is the equation that describes the electric field component of this electromagnetic wave, but there's also a B field component, right? The good news is it's the exact same equation. Because these waves are in sync, they're in phase, the wave number and the frequency for both of them are going to be the same. Right? So that's nice, because that means I can immediately write down B, but it's not B of Y, right? Because B and E have to be mutually perpendicular. So there is no Y component of B if there's a Y component of E. So this is going to be Z of X and T is equal to B naught cosine KX minus omega T. Alright, these are the equations that tell you exactly how the electric and magnetic components of light oscillate in space and time. Okay. I'll leave these up here and then I'll give you an example problem to show you that it's really, it's almost trivial to answer problems with it at this point. Bigger chalk. Alright. Sarah, give me like 10 seconds, let me grab a piece of chalk. Alright, suppose I give you this equation. And I'm making up these numbers, and they probably won't be right, so don't put a lot of stock in my numbers. Yeah, those are definitely not. I'll tell you why these numbers won't work, but I'm just making them up to give you an example of how this works, right? So this would be the actual equation that would describe the electric component of some traveling electromagnetic wave, right? At this point, you can just read off a bunch of information. If I were to ask you, what is the maximum value of that electric field, what would you say? 3,500 volts per meter, right? You just read it off. You match it up. E naught is the amplitude. That's the maximum value. 3,500 volts per meter. What is the angular wave number of this wave? It's 500 per meter. Right? It said that what that says is for this wave there are 500 cycles in every meter. And what about the frequency? What's the angular frequency? 35,000 hertz, or inverse seconds, or per second, whatever. That's the angular frequency. You didn't find the linear frequency. Well, yeah, if you know that this equation is true. Right? Which one did you find? Which one is 35,000? divided by 2 pi to find the linear frequency, right? So that's what I mean. There's a lot of talking, and there's a lot of concepts to understand, but the actual problems here are really not bad. Okay? Questions about that? Now, here's why these numbers will never work. So I'm going to erase this. This is just an example. Here's why these numbers will never work. There's a relationship between the spatial and temporal aspects of, well, anything, right? But especially of waves. Waves propagate through space and time, right? That means there has to be a relationship. You actually, whether or not you know it, you already know the relationship between temporal and spatial. It's as simple as this. Right? Spatial, temporal. In this universe, you really don't get one without the other. If you're going to have a delta x, you have to take in some delta t, right? There has to be a correspondence between the two of them. So with that in mind, let me show you the explicit relationship here for any wave. The frequency, now this is the linear frequency, times the wavelength, right? The actual distance of one cycle in the spatial region is equal to what we call the wave speed. You can do simple calculations with this. If you go to a baseball game, you sit in the cheap seats, right? You see them hit the ball, and then like 5 seconds later, you hear the sound. You can use stuff like that to determine the speed of sound in air, and then that tells you the frequency of that. If you have any two of these quantities, you can find the third one. For light, though, light's an interesting one because we have a special name for the speed of light. At least the speed of light is vacuum for light, or for electromagnetic radiation, I should say. For EM waves, F lambda is equal to C. C is just the special name we give to the speed of light in vacuum. It's about 8.99 times 10 to the 9th meters per second. Really fast. 186,000 miles per second if you're an English imperial guy. It's really fast. But the wave speed equation still works. That's why I knew those numbers couldn't work, because you're never going to get the speed of light with the numbers I gave you. But what this means, though, is I could give you a problem which only has one of these, and ask you to find the other one. That's this equation that gets you there. So the wave speed equation turns out to be pretty important. Okay? There's some other interesting relationships between these two. That's actually not the only way to get the speed of light out of this. At any time, the magnitude of the electric field divided by the magnitude of the magnetic field gets you the speed of light. This is true, usually. The problem comes because in both of these, since they're oscillating, there are points when both of them are zero, right? And that leads to some problems, because if the B field is zero, then this equation is nonsense. You can't divide by zero, right? I know how to divide a pie into 1 pieces and 2 pieces and 3 pieces. I don't know how to divide it into 0 pieces. That doesn't work. You have to eat it, right? You can't divide it. So this doesn't work when it's zero. So to avoid that, we just pick out a particular value, most notably what we have in the equation, the amplitude values. So usually you have this. So look at what I can do. I can give you an equation for one of these and say, okay, well, you know what, let's just do it. We have time. Let's work it together. I'll leave this up and I'll give myself some room and then rewrite this stuff. relative equations here. Given what I've written on the board, can you find out what omega is and write down the equation for the magnetic component of this same wave? All right, let's see how we can get it. Well, I've got the wave number there, right? And I've got, which I know, so if I know the wave number, that means I know the wavelength because 2 pi is just a constant. Okay. So what I need is F. So let's see if we can relate these two using this equation. Lambda F is equal to C. Now what I'm going to do is rearrange some stuff here. Just rearrange these definitions. Okay? So let me make those substitutions. If the frequency, the linear frequency, is omega over 2 pi, and the wavelength is 2 pi times the wave number k, I can put that in here. That's going to give me 2 pi k. That's the wavelength. Frequency is omega over 2 pi. That's nice. My 2 pi's are going to go away. And this leaves me with omega k is also equal to c. Oh, I'm sorry, I'm so sorry. That did not look right. Yeah, it's because I wrote that down wrong. My apologies. It's this one. It's not lambda over 2 pi, it's 2 pi over lambda. That's my bad. When I got there, I knew that wasn't right. Okay, let's try that again. Lambda is 2 pi over k, so let me just start here. 2 pi over k times omega over 2 pi. Alright, so I made my correction. Let's go away. This is what I was expecting. Omega over k is equal to c. This is nice because I always know what c is, right? And I know what k is, so now I just need omega. This means, of course, omega is equal to k times c. So if I'm going to use the value, and I will use the value, c is equal to 9 times 10 to the 9th. It's closer to 8.99, but your formula sheet has 9, that's fine with me. So if I do that, you know what I'm doing. I'm going to go to Wolfram Alpha because that's more robust. If you guys have not discovered Wolfram Alpha, you should try it. Online, basically an online version of Mathematica. So the speed of light c times the wave number k, which is 3,500, which gives me 85,625 and change hertz or per seconds, either way you want to write it. So the math here, apart from my mishandling of the equation, the math here is relatively simple. You just have to know what you're reading off. Okay? Does this make some sense? Okay. So let's start to answer the question. What I can now do is, instead of omega, I can put in 85,625 hertz times t. Okay. Now, if if I'm going to write down the magnetic equation, not Y, well, it's going to be some B naught, which I'm going to figure out in a second. But then this is nice because because these waves are in phase, everything else is the same. Their temporal and spatial frequencies are the exact same. So cosine 3,500 per meter times x plus 85,625. I'll write hertz here just to get you used to seeing both of those notations. So now I just have to figure out what B naught is. This comes to my rescue right here. E naught over B naught is equal to C. So I'm out of room for that. But this means, of course, that B naught is equal to E naught over C. E naught is 5,000. Did I get this? You know, I'm typing something wrong. Oh, I think I did. Gosh, I'm sucking today. Yeah, okay. My apologies. I didn't type in something wrong. I just didn't type in something at all. My apologies. So this number is wrong, but does everyone see the process? That's what I'm concerned about. Okay, sorry. I just got the wrong number. This is 3.5 times 10 to the 12th. Significant difference, right? The process was right, I just got the number wrong. So you see my thing today. 3.5 times 10 to the 12th. Okay. Now, we got E naught divided by C. E naught is 5,000 volts per meter divided by I get about 5.6 for B naught times 10 to the negative 6, and that's going to be in Tesla. Right. And now I'm done. Apart from the typos and bad copying on my part, I don't think that's that intense. Does anybody have questions about how we proceeded there? All right. What's the propagation direction of this wave? No, not X. Oh, yeah. Yes, X. How did you get that?
Because it's your spatial.
E field is oscillating in which direction? Y. B field is oscillating in which direction? Only other direction left is X. I thought I wrote, yeah, I didn't write X here, right? You can also get it from here. This is your propagation direction. Okay? Man, my brain really checked out for about 15 minutes. Are we okay here? I had not planned on discussing waves at this level, but that's okay. So I'm fine by the seat of my pants. That's never a good idea. Are we okay here? Questions about this? All right. If not, say so. Okay. Now, we've seen a couple of expressions also for energy density. Energy density turns out to be cumbersome when you're talking about things like capacitors or inductors. But when you're talking about electromagnetic waves, which are not confined to certain regions, the density turns out to be the right way. Like if you're talking about a capacitor, there's a definite volume in between the plates. So why not just talk about the energy? If you're talking about the energy in an inductor, there's a definite volume inside that coil. Why not just talk about the energy? But for a wave, you can't locate a wave, right? Think about it. The waves coming from these light bulbs. Where is it? What's in this room? Oh, okay, that's still not specific. Even something like a water wave. Go to the beach. Where's the wave? It's right there. Well, isn't it kind of right there? Right? Waves have no definite location. That language doesn't even make a whole lot of sense. So, to talk about the energy of a wave is somewhat cumbersome because we can't really determine the volume. We can talk about the energy per unit volume, though, the energy density. That turns out to be more facile for us. So we saw a couple of equations for energy density. Energy, remember this is a lowercase u, which is the standard for energy density. Uppercase U would be potential energy, lowercase is density. The energy for an electric field, we saw this. We also saw the energy density for a magnetic field as this. Now, to turn this into something that we can use for electromagnetic waves, we've got to recognize that this is going to be a maximum E field for us. A maximum B field. When we looked at these, we looked at them in the context of steady fields, E field and B field being steady. But that's not the case for electromagnetic wave. These are oscillating fields. So we're going to pick off the maximum values, E naughts and B naughts. You can put these two together in interesting ways to come up with yep. Well, I lost it. Where did it go? Well, there's a couple of interesting ways we can put them together. 2 seconds. I'm rethinking how I'm going to present this. Yeah, okay. I'm switching gears off, I say. My apologies if this isn't clear. If it isn't clear, please just say so. I'm happy to do that. These are the energy densities associated with the electric fields and B fields for the electromagnetic waves. I'm just going to put a knob here for both of those. Okay. Now, let me introduce you to one more mathematical construct here, which turns out to be important. It's called the pointing vector. I believe Pointing's first name was Stephen, which is why this has an S. I believe that's the truth.